Hello, everyone, and welcome to this deep dive into one of the most elegant and powerful generative models in modern deep learning. Today, we are exploring the Variational Autoencoder, or VAE, a foundational architecture that teaches us how machines can not only copy the world but truly create new things. Our journey is titled VAE, the art of generation, and it is indeed a tale of two architectures. We will start with a seemingly perfect apprentice, the standard autoencoder, which is masterful at replication. But we will quickly discover that this apprentice harbors a deep, fatal flaw in its soul. The rest of our time will be spent learning how the variational autoencoder, the master, takes the original design, reforges it with two essential secret disciplines, and unlocks genuine, continuous generative capability. This story is crucial to understanding how we moved from simple compression tasks to the stunning image and data generation tools we use today. We are going to break down the mathematics and the architectural shifts that govern the VAE, explaining complex ideas like the reparameterization trick and KL divergence loss in intuitive, visual ways. So let us begin our training and learn the path to generative mastery. Our journey through the VAE architecture is structured into four distinct acts, which we call the list. First, we examine the autoencoder, the apprentice. This network is brilliant at its core task, copying input data, but we find that despite its perfect copies, it possesses a flawed soul for generation. Second, we dive into the ghost in the code. We will uncover the fatal weaknesses inherent in the autoencoder's design, specifically how its internal map of the data, known as the latent space, is broken and unusable for creating novel content. Third, we introduce the master's blade. This is the variational autoencoder, the new weapon forged to overcome these flaws, built upon two secret disciplines, two critical additions to the loss function and the encoder's output. These disciplines transform the network from a mere copier into a true creator. Finally, we explore the five-point palm technique. This is the moment when the VAE achieves true generative mastery, demonstrating how its organized and continuous latent space allows for controlled creation, seamless interpolation, and even vector arithmetic, giving us unprecedented precision over the output data. Follow the flow in the diagrams as we proceed, from the simple encoder and decoder through the discovery of fatal weaknesses in the hidden layer to the adoption of secret disciplines, and finally, reaching the ultimate goal of generative control. This map guides our entire presentation. We begin with the standard autoencoder, the apprentice, and the forgery. To understand its function, we use the analogy of the master calligrapher and the infinite scroll. Imagine an apprentice who represents the encoder. The encoder's job is to look at a complex input, like a hand-painted calligraphic character, and distill its entire essence, the stroke weight, the curve, the posture, into a single, potent set of coordinates. These coordinates lie on an imaginary infinite scroll, which we call the latent space. This is the compressed, essential representation of the data. Now, a master artisan, who represents the decoder, can take only those compressed coordinates from the scroll. The master artisan must then perfectly replicate the original complex character from scratch. The core function of the autoencoder is this two-part process, compression followed by perfect reconstruction. The goal is to ensure the output image is as close as possible, pixel for pixel, to the original input. This entire mechanism is trained on one primary objective: fidelity. The network is judged on its ability to faithfully copy the original. While this is an invaluable skill for dimensionality reduction and data compression, we will soon see that perfect copying does not necessarily translate into the ability to create new, never-before-seen data. The autoencoder is capable of creating a flawless forgery. To demonstrate this, we train a standard autoencoder on the MNIST dataset, which consists of thousands of handwritten digits. The network's sole purpose is simple: compress each complex image into a much smaller, two-dimensional vector in the latent space, and then expand that vector back into the original image. The results, as shown here, are impressive. The reconstructions in the bottom row are nearly identical to the originals in the top row, even after passing through the drastic compression bottleneck. This proves that the autoencoder has learned an incredibly powerful, compressed representation of what a 7 or a 4 or a 6 truly is. It has successfully captured the core features necessary for replication. However, this success hides a fundamental limitation. The autoencoder's skill is purely replicative. If we ask it to do anything other than reproduce something it has already seen, the system breaks down. It knows how to draw a 7 and it knows how to draw a 6, but it has no conceptual map for what exists in the space between 7 and 6. This limitation is the seed of its failure as a generative model, leading us to investigate its latent soul. This brings us to Act 2, the ghost in the code, where we examine the autoencoder's fractured soul. The problem lies not in the encoder or the decoder themselves, but in the disorganized structure of the latent space. When we take the thousands of latent space, coordinates the encoder produces for our MNIST digits, and plot them on a two-dimensional graph, a troubling picture emerges, visible in the illustration. The autoencoder has done a great job grouping similar digits. All the 7s are clustered together, the 1s are clustered together, and so on. But it has done so by creating distinct, isolated islands of data. The critical realization here is that the vast spaces between these brightly colored islands are a meaningless void. The network was only incentivized to put similar data points close together. It was never penalized for leaving huge gaps between them. While the autoencoder can perfectly replicate any point inside one of these islands, it has no coherent, continuous understanding of what a digit is across the entire map. It lacks a continuous sense of digitness. This fractured, non-continuous structure is the source of the autoencoder's fatal flaws, preventing it from ever achieving true generative power. If we want to move smoothly from one concept to another, like transitioning a 1 into a 2, the current map is useless. The fractured structure of the latent space results in 3 fatal flaws that destroy the autoencoder's potential as a generative model. The first flaw is the unbalanced form. The clusters of data are scattered haphazardly across the space. There is no central point, no uniform density, and no defined boundary. If a new user wanted to generate a brand new digit, where would they even begin to sample a coordinate? There is no intuitive center to start creating from. The second flaw is the empty spaces. Vast, unlearned gaps exist between the clusters. The path between the island of 4s and the island of 9s is a sheer void, a region where the decoder has learned nothing. The autoencoder was never given any reason to make these intermediate regions meaningful because the training data never mapped to those spots. The third and most critical flaw, which exposes the system's failure, is the monstrous creation. If we dare to sample a random point from one of these empty, unlearned spaces and feed it to the decoder, the result is a monstrous, unrecognizable form. As the diagram illustrates, the output is blurry noise, a phantom image that mixes meaningless features. The decoder simply has no idea what to do with a coordinate that does not belong to a cluster it has learned. It is like asking a dictionary program to define a word that does not exist and has never been used. This inability to generate anything meaningful outside of its training distribution confirms that the autoencoder is a great forger, but a terrible creator. It needs a soul, and that soul is discipline. This brings us to Act 3, the Master's Blade. The Variational Autoencoder, or VAE, solves the autoencoder's structural flaws with a profound architectural shift, moving from a point to a presence. In the standard eye, the encoder maps the image to a single, precise point Z in the latent space. This precision is the eye's undoing, as it encourages the isolated island formation. The VAE changes this entirely. Instead of outputting a single point, the VAE's encoder maps the input image to an entire region of possibility, a Gaussian probability distribution. This distribution is defined by 2 separate vectors that the encoder now outputs: z-mean, which defines the center or the location of the distribution, and z-log-var, which defines the logarithmic variance or how fuzzy or spread out the distribution is. The encoder no longer says, the image is exactly at this coordinate. Instead, it says, the image is likely somewhere within this cloud. This shift from a single, deterministic point to a probabilistic, fuzzy cloud is the VAE's fundamental innovation. It introduces randomness and uncertainty into the encoding process. This single change sets the stage for the 2 disciplines necessary to organize the latent space, transforming the VAE from a simple copier into a truly generative model, capable of creation and control. Discipline I is the probabilistic stance. By mapping every input image to a distribution instead of a single point, the encoder becomes stochastic. To reconstruct the image and train the network, we must sample a single point, z, from this generated distribution and pass that sampled point to the decoder. The mathematical representation of this sampling process is shown on the slide. Z equals z mean plus the exponential of half of z log var multiplied by epsilon, where epsilon is random noise drawn from a standard normal distribution. This is often referred to as the reparameterization trick. The crucial insight of this trick is that it allows us to separate the deterministic parameters, z mean and z log var, from the random element, epsilon. Keeping the random component separate allows the training gradients to flow back through the network effectively, even though we are sampling randomly. The pressure this introduces is immense, because the decoder must be able to reconstruct the image successfully from any point sampled within the probabilistic neighborhood. It is forced to learn that all adjacent points must decode to similar, well-formed images. This pressure is the healing mechanism that smooths out the edges of the clusters and fills in the catastrophic empty spaces, thus creating a continuous latent space. Discipline II is the way of KL divergence. The VAE's revolutionary architecture is governed by a new dual-component loss function that enforces both performance and discipline. The first component is the reconstruction loss. This is inherited from the standard I and is essential. It ensures the blade must remain sharp. The decoded image must still be a faithful, sharp reconstruction of the original input. The second, entirely new component is the KL divergence loss. This term measures how much the encoded distribution, defined by z-mean and z-log var, differs from a standard normal distribution, which is centered perfectly at the origin. This acts as a powerful regularizer, forcing all the encoded distributions to be pulled toward the center of the latent space. The KL divergence enforces the discipline necessary to prevent the formation of scattered, isolated islands. If the KL loss is high, it means the clusters are too far from the center or too tightly packed. By minimizing the KL loss, the VAE is forced to organize the latent space into a single, uniform, dense cloud centered at zero, resembling a proper Gaussian distribution. The visual change is dramatic. The sparse, chaotic islands of the standard I are compacted and smoothly merged into a single, functional universe of data. This organized space is the absolute key to true generative power. The combination of the two disciplines results in the 5-point palm technique, achieving a universe in harmony. After training a VAE using both the reconstruction loss and the KL divergence loss, the latent space is fundamentally transformed. We can visualize this transformation by comparing the I's results on the left to the VAE's results on the right, using a dataset of stylized fantasy portraits, for example. The standard autoencoder still yields the I, a fractured soul. The data is clustered into separate, non-overlapping regions, unusable for interpolation or random generation. In contrast, the VAE yields a universe in harmony. The probabilistic encoding and the KL divergence discipline have completely eliminated the flaws of the standard autoencoder. The new latent space is continuous, meaning there are no empty voids. It is dense, meaning the data fills the volume uniformly, and critically, it is centered around the origin. Every point in this new, ordered universe is now meaningful. If we sample from this space, the decoder will know exactly how to handle that coordinate and produce a valid, high-quality image. This structured, predictable distribution, which mirrors the mathematically ideal standard normal distribution, is the ultimate key to true generative power and control. With the latent space now structured like a standard normal distribution, continuous and centered, we unlock the VAE's ultimate capability, creation from the void. This is the simple yet profound process of generating entirely new content. It requires just 2 steps. First, we sample a random vector, z, from the standard normal distribution, which is centered at 0. Because our VAE has been disciplined by the KL loss, we know that this point will correspond to a valid, meaningful concept within the learned data universe. Second, we simply pass this sampled vector through the trained decoder network. The result is a novel, high-quality image that has never been seen before, yet perfectly conforms to the style and attributes of the training data. Below are examples of character portraits generated by sampling random points from the VAE's latent space. Notice that every single face, figure, and costume is unique, but they all adhere to the consistency of the fantasy style the model was trained on. This is the definition of generative mastery, the ability to pull meaningful, brand new information directly from a random vector, confident that the decoder has learned a continuous, meaningful map of possibility. The organized and continuous latent space of the VAE allows for another astonishing capability: the art of vector arithmetic. This means that concepts and visual features, such as beard or elven ears or female, can be isolated as vectors within the latent space and then added or subtracted to existing image embeddings. This is the ultimate expression of control over creation. Consider the diagram illustrating a latent space equation. We start with the embedding for the warrior character, Z Warrior. We then wish to modify the character to remove his beard and add elven ears. We find the vector difference representing elven ears, V elf ears, and add it. We then find the vector difference representing beard, V beard, and subtract it. The resulting new vector, Z new, is then passed through the decoder. The output is a character who retains the core attributes of the original warrior, such as his armor and expression, but now possesses elven ears and lacks a beard. This level of precise manipulation shows that the VAE has done more than just group data. It has learned the fundamental, linear relationships between features. We are not just creating, we are precisely manipulating the core attributes of a creation using simple addition and subtraction. Perhaps the most definitive proof of the VAE's success is the unbroken path, demonstrated through smooth interpolation. Since the continuity of the VAE's latent space is guaranteed, the path between any two encoded points is entirely meaningful. If we take the latent vector for portrait A and the latent vector for portrait B and decode points along the straight line that connects them, we can generate a seamless morphing sequence. Look at the sequence of portraits below. The transition from the old, bearded wizard on the left to the young female rogue on the right is fluid and gradual. Features like the color and length of the hair, the presence of facial hair, gender characteristics, and even expression change simultaneously and smoothly, frame by frame. If we tried this with a standard autoencoder, the morph would likely pass through the empty spaces between the data islands, resulting in blurred, noisy, monstrous frames. The VAE, by contrast, ensures that every intermediate point along the path yields a valid, high-quality image. This fluid, continuous transition is irrefutable evidence that the latent space is not fractured by empty voids. The VAE has built a continuous, traversable map of all possible outputs, confirming its mastery over generative modeling. We conclude by returning to the core distinction: the path of the master. The standard autoencoders are masterful forgers. They excel at compression, dimensionality reduction, and perfect replication. However, their soul, the latent space, is fractured, barren, and utterly incapable of true, controlled creation. They are deterministic copiers. The variational autoencoders, or VAEs, are true generative artists. They embrace probability through the probabilistic stance, and they embrace discipline through the KL divergence regularization. By forging these two principles together, they create a continuous, rich, and usable universe of possibility, centered around a predictable distribution. Mastery of this technique unlocks a power that goes far beyond simply creating novel images from nothing. It provides the ability to traverse the space of data, to manipulate its essence with precision, and to control the attributes of the generated output mathematically. This foundation laid by the VAE architecture is a critical step in the evolution of modern generative AI, setting the stage for even more complex models that came later. Thank you for joining us on this journey into the art of generation.